Ordering at a restaurant, you don't stand frozen at the table until your food arrives. You talk, you drink, you exist. A database doing synchronous I/O, it just waits. And that one difference explains why modern databases are built completely differently. Asynchronous I/O means a program can send out a request, read this file, fetch this data from disk, and then keep doing other work while it waits for the answer to come back. It doesn't block. Synchronous I/O does the opposite. It sends a request and stops dead until the response arrives. The restaurant analogy is almost perfect here. A synchronous waiter takes your order, walks to the kitchen, stands there until the food is ready, then brings it to you. An asynchronous waiter takes your order, drops it off, and immediately goes to take 3 more tables. Same amount of food gets cooked. Far more gets done in the same time. If you've ever written a Python script that queries a database and noticed it feels sluggish, or wondered why some databases handle thousands of simultaneous users while others buckle under 10, this is a big part of the answer. The problem shows up in 2 concrete places. First, in applications. A web server handling user requests can't afford to freeze every time it reads from a database. If it blocks on each request, users queue up. Second, inside the database itself, reading data from disk is slow relative to CPU speed, orders of magnitude slower. A database that waits synchronously for every disk read is leaving most of its processing power completely idle. This is the I/O bound problem. The bottleneck isn't computation, it's waiting. When your program issues an I/O request, say, read this chunk of data from disk, that request goes to the operating system. The OS handles the actual hardware interaction. In synchronous mode, your program hands off that request and then just sits there doing nothing until the OS hands the data back. Asynchronous I/O breaks that waiting apart from the work. Your program registers a request, moves on to other tasks, and gets notified or checks back when the result is ready. The mechanism that manages all of this is called an event loop. Think of it as a traffic controller sitting at an intersection, constantly checking, is this request done yet? What about this one? When something finishes, it routes the result to whoever was waiting for it and keeps moving. In Python, this is what the async and await keywords are doing. When you write await, you're telling the event loop, I'm pausing here, go do something else, and come back to me when the data arrives. The program isn't sleeping, it's just not blocking the lane. And if you like understanding how this stuff actually works, Stack Future breaks down something new every day. DuckDB specifically was built with asynchronous I/O as a core design assumption, not an afterthought. When DuckDB reads columnar data from Parquet files or object storage like S3, it can issue multiple read requests simultaneously and process the results as they land. Instead of reading one chunk, waiting, reading the next, waiting. That parallelism inside the I/O layer is a significant reason DuckDB performance on analytical queries is fast even on a laptop. Imagine you're running a data pipeline in Python. You're querying a DuckDB database that's reading from several Parquet files stored on disk. Each file read takes a few milliseconds. Tiny, right? Multiply that by a query that touches 40 files. Synchronous. You read file 1, wait, read file 2, wait. 40 sequential waits stacked in a line. Asynchronous, DuckDB issues read requests for multiple files at once, processes whichever chunks arrive first, and keeps the CPU fed with actual work the whole time. The difference on a large analytical query can be the gap between a result in 2 seconds and a result in 12. The data is identical. The computation is identical. What changed is whether the system spent most of that time actually working or standing at the kitchen window waiting for the food. This is also why Python async programming has become so central to building anything that talks to a database, an API, or a file system at scale. Asynchronous I/O isn't about doing things faster. It's about not wasting time waiting. A system that can issue 10 requests and handle whichever finishes first will always outrun one that issues them one at a time, no matter how fast the hardware is. That's the core idea, and it's the design principle behind DuckDB's speed and Python's async model. If this clicked, the natural next step is understanding how connection pooling works, because async I/O and pooled connections together are what let a single server handle thousands of users without collapsing. If this video helped, a like genuinely helps other people find it.